So, just to know my audience, how many are from the mathematics department here? Yeah. Okay, that's more than half. Okay, how many from computer science? Anyone from physics? Administration? Economics and administration, yes? Good, okay. So, of course, I try to talk about a technical topic without being technical. At some points I will be a bit technical, but I try to avoid the technicalities and try to give a more sort of philosophical idea about computational mathematics. Computational mathematics is a part of a much bigger endeavor called scientific computing, computational science. Let's just start by putting things in perspective, say something about computational science. Computational science is, in the natural sciences, considered to be the third way. You have the traditional ways of theory and experiment, and computation is the third of the approaches to understanding nature. Like here, if you want to understand structural properties of mechanics, then you use finite element methods. That's an example of computational science, how to do these kind of things. And where did this computational science start? I think in a way it started with Kepler's understanding of the solar system. So I have three years here. It's 1605, 1614, and 1618. Kepler had all the observations of the solar system from Tycho Brahe, the Danish astronomer, and he wanted to find the laws governing the planetary motion. So already in 1605 he found the first and the second law. The first law says that the planets were moving in elliptic orbits with the sun in one of the foci. Second law says that the radius sweeps equal areas in equal amounts of time. And then there's a gap of 13 years from the first two laws until the third law. And what happened in this gap? In this gap came John Napier, who invented the tables of logarithms. The tables of logarithms was to Kepler a computational device, because he could use them to look up the logarithms, add logarithms, and do the anti-logarithm, and then use this as a way of computing products of numbers. So Napier's tables were at those days a computer that could really help Kepler solve his problems. It did more. It helped him also organize the observations. So the third law, 1618, was directly inspired by this table of logarithms, where if you plot the logarithms of this in a log-log plots, the semi-major axis of the orbits versus the orbital periods, you get an absolutely straight line with an inclination of 3/2. So this is something that Kepler didn't see until he got this insight via the logarithms. No, that was too far. So no, there was also a fourth law of Kepler. That was his view of the distances in the solar system. There were 6 planets, and he had this idea that there were 5 regular Platonic solids, and he could explain the distances in the solar system by fitting these 5 regular Platonic solids between the orbits of the planets. He thought himself this was a great idea, but it's not really established as a physical law. It's more like a coincidence, perhaps. Second example of computational mathematics. This is a Norwegian example. So these two guys, that's Christian Birkeland and Carl Sturmer. Birkeland, physicist, was interested in the theory of the northern lights, or the polar lights, aurora borealis. And he had this theory that it would be explainable by particles from the sun. That was a novel theory about 100 years ago, or 120 years ago. So to try this, he constructed a vacuum chamber with a charged magnetic ball inside, and he was shooting electrons on this, and saw that he got, by putting luminescent material on the ball, he got these polar lights in laboratory. Carl Sturmer started as a professor of pure mathematics, interested in number theory and analysis. And he became interested in this problem of computing the orbits of particles moving in the magnetic field. So around 100 years ago, he devised a numerical method to integrate the orbits of these charged particles. And he needed a computer. So what he did was to train his students to compute the orbits. And a good trained student could move a particle 3 steps per hour. They spent something like 4,500 hours computing 400 or so orbits. And this was a way of explaining how much energy was needed to get northern lights on different latitudes, a lot of things like that. History of computers, as I said, in the 300 years from Napier until 100 years ago, logarithms was the main computational tools around. We had this, many of you recall it from the old days, computational rulers. Then in the 20th century, a computer, in the first half of the 20th century, a computer was a person doing computation like the students of Sturmer, or a room full of women like here doing really hand computations. This is Margaret Hamilton. She was more a programmer. She was doing the orbital lander program for the Apollo program and got the Presidential Freedom Award from Obama. But I think the view of computers at that time, people doing computing, it was a low, it was not the highest respected area of mathematics to do computations like that, which we will see later also. 1955, that was the time when the first electronic computers were around, MANIAC, mathematical analyzer, numerical integrator, and computer. And then from then things exploded with this Moore's law, exponential growth over more than 5 decades, and with a doubling of every 18 months or so. Fantastic increase in speed. And if you take something like an iPhone, it would have been on the list of the 500 fastest computers in the world if it was in 2007 or so. And if you go further back, it would have been faster than 1995, when I was already well beyond my PhD. It would have been faster than the fastest computer in the world. So this development is, of course, fantastic, and has given us this superpower of computations. This MANIAC computer, one of the first experiments to be done numerically was this experiment of Fermi, Pasta, and Ulam from 1955. And they had this idea that they wanted to check ergodicity. And so ergodicity is this theory that a system would spread all over the phase space eventually if you integrate for a long time. And they put up a numerical computation of nonlinear strings, a system of balls in nonlinear strings. To the big surprise, what they found was that this assumption that it would equally spread on all energies and all modes of the system, it was not working like that. It was more like this system was miraculously returning essentially to something like the initial condition. It was a periodic solution. And this was probably the first manifestation of integral nonlinear dynamical systems. There was a physical observation of solitons from the beginning of the 19th century where a person, now I forgot his name, he observed this wave in the canal in England, and it's this solitary wave that was moving without dispersing. But this was a big surprise, and this was really the birth of nonlinear science. That was a numerical experiment. There is a twist to this story, because if you read their paper, they thank a fourth person. The fourth person is Merit Tsingo, and she was the one doing all the numerical experiments. And all the numerical work in this was done by her. And she was only thanked in the acknowledgement of the paper. So many people nowadays think that we should call it not FPU, but FPUT, because nowadays it would have been natural to include that person also. That's a significant part of the work, is also to do really the experiments. I want to move to the core topic, which is computational mathematics. Computational mathematics is the central area of computational science. It's where we develop algorithms. It's an activity in the borderland between applied mathematics, pure mathematics, and computer science. I would really like to focus on some overall bit philosophical aspects of computational mathematics. In the 20th century, there was developing a big gap between applied and pure mathematics. And I'm going to discuss why this gap, the reason for the gap. And my claim is that computational mathematics is an activity that is unifying mathematics. That will be one of my statements here, that it's bringing together different areas of mathematics. It's also bringing together computer science into the same kind of activity. So that's one thing I will discuss. And the other thing is the role of looking at geometric structures when you do discretizations. So what is this gap? The gap between pure and applied mathematics. I think in the 19th century, there was not such a big gap between pure and applied mathematics, but in the 20th century, the goals are different in pure and applied mathematics. In pure mathematics, the main goals is to classify mathematical structures and relations between different mathematical structures. And so there was a need to develop mathematical tools to understand geometric structures, algebraic structures, and general structures that are sort of qualitative without relying on particular representations of objects. So the tools of pure mathematics are abstract representations of geometric objects in a language that is independent on particular coordinate systems. So that's a view that you can understand geometry without having to put particular coordinate systems on the geometry. Or in another way, that all coordinate systems are equivalent. Category theory, a language where you look at objects via the relation between the objects and other objects. Then techniques of linear algebra and global analysis and differential geometry. So a lot of these tools here are abstract mathematical tools aimed at studying structures, answering questions about existence, uniqueness, qualitative qualifications of classification of mathematical structures. That's very different from applied mathematics. I was trained as an applied mathematician and as a numerical analyst. Our goals was to study concrete physical and mathematical problems, to design efficient computational algorithms to solve these problems. That is a basic problem we are dealing with, how to efficiently solve problems coming from applied sciences. What are the tools? Concrete representations, good basis, good ways of presenting objects in such a way that you can efficiently compute on these structures. Finding a good basis for linear spaces, efficient data structures for accessing the data in supercomputing, and this kind of. So it's a very concrete goal. It's based on representations, on concrete representations, and it's based on algorithms working on concrete representations. Computer science has, in my opinion, and I was associate professor and professor in computer science department for 14 years, and I had a lot of discussion with people in computer science, and I think that in theoretical computer science they have an interesting take on dichotomy between the abstract and the concrete. The goals of computer science is to study, it's more theoretical than applied mathematics, or computational mathematics. It's the study of general structures of computational processes. Structured programming languages, efficient algorithms based on concrete representations. But the tools are things like structured programming languages, category theory to understand languages, complexity theory, object-oriented programming, and the combination of abstract specifications and concrete representations. I'll try to be more concrete on what I'm talking about. But let's first go to why mathematics became so abstract in the 20th century. So what's the role of abstractions in mathematics? Abstractions discard non-essential features of a concrete mathematical structure and focuses on definitions of its fundamental properties independently of concrete representations and realizations. Abstractions unify different related structures and as concrete examples of an underlying abstract object. So the difference between the abstract and the concrete is as the difference between describing what is something and versus describing how to do something. This is a more algorithmic approach. This is the basic structural approach. So be very concrete. Let's think about something that all of you should know. Linear spaces, vector spaces, matrices. Concrete. A vector is a collection of coordinates, n numbers, where we define the operations as plus and dot product and tensor products by saying what it does on these coordinates. A matrix, collection of m times n numbers in an array, where the basic operations such as matrix multiplication and inverse is defined in terms of how it's expressed in the coordinates. In this concrete view of linear algebra, there are different realizations of the same structure. We didn't really say what is this structure, but there are different ways of realizing it. We could realize a matrix as a dense matrix. In computational mathematics, they're often full of zeros, so it could be represented as a sparse matrix where we don't store the zero numbers. We can represent in different bases, and often in computational problems, there's a search for a good basis. We can do many things, many tricks, like partitioning the matrices in blocks, and then look at various algorithms for doing things like matrix products and linear solves. Abstractly speaking, vector spaces are just spaces with satisfying they have an addition and they have a scalar multiplication such that various laws are fulfilled. Instead of matrices, you speak of linear operators. And if you have linear operator, of course, you can represent it in terms of a basis. Many constructions in linear algebra can more abstractly be described in terms of diagrams like this, where you say that this object of doing tensor products of linear spaces is described by some diagram saying how this tensor product should respond with respect to mappings coming in and out of this object. This is a way, I'm not going to tell you details, but this is a way you can describe an object by what is coming into it, what is going out of it, and how this in and out relates. That is a very general way of doing things that in principle works for essentially, I would say, essentially all of mathematics. That is the basic things of category theory, that you study mathematical structures by things coming in and out of the object. That is, to computer scientists, it's a very natural notion. So she wrote a book on abstractions in mathematics. A powerful aspect of abstraction is that in many different situations become the same, if you forget some details. Eugene Cheng. Sir Michael Atiyah was interested in the role of abstractions for the survival of mathematics, I would say, in the sense that he was asking the question, how come that a student of mathematics can learn centuries of accumulated knowledge in a couple of years? That is quite amazing, that it has taken centuries to develop areas of mathematics, and then we teach it to the students in 2-3 years. And to Michael Atiyah, this is the only way this can be done is by abstraction, so that essential details, essential structures prevail, and unnecessary details is not needed to be taught. The aim of a theory really is, to a great extent, that of systematically organizing past experience in such a way that the next generation, our students and their students, and so on, will be able to absorb the essential aspects in as painless a way as possible, and this is the only way which you can go on cumulatively building up any kind of scientific activity without eventually coming to a dead end. So the idea is if you don't eventually pull out the essentials of the mathematics, then it will become so big, this body of knowledge, that it's not possible to convey it to the next generation after some generations. So what happened to pure mathematics? Many things happened to the abstraction of mathematics in the 20th century. Concrete things like symmetries, perhaps in the 19th century, symmetries were really the reflections and rotations of an object that left it invariant. This is, by the way, the maze in the Botanical Garden in Bergen. This is another topic I have designed a maze, a labyrinth in the Botanical Garden. This is the design of the Botanical Garden labyrinth in Bergen, based on symmetries. But in the 20th century, symmetries were abstracted from symmetries as operations on an object to the study of groups as the abstract notion of symmetry, and tying it to concrete objects by the action of a group on a concrete object. The other important tool developed in the 20th century was the global analysis or manifold view of differential equations, where you consider the essentials of the domains where differential equations live by looking at what are really the important things about the spaces where we model our differential equations. Basic things is that we have points. In the point we can talk about velocity, the tangent vector. We can talk about mappings between manifolds, and we can put more structure on this basic mathematical object, differential manifolds. The idea is now that you could put coordinate systems. If you have an area here, you can map it down to a flat chart. And you can induce mappings between linear spaces here from given coordinates on the domain and the codomain. For this to be a geometric, the things you define to be a geometric object, it must be essentially independent of the given coordinate system. So you're allowed to put coordinates on the domain, but the basic geometric information should be the same regardless of what coordinates you use. So that's the basic idea of global analysis. That is a setting in more abstract mathematics for studying differential equations. This is very different from the computational mathematics approach. As a student of numerical analysis and computational mathematics, I never heard about this kind of structures. Algebra, same story. The classical view of algebra was the focus on existence, uniqueness, and classification of algebraic objects, developing machinery of lots of techniques and languages to discuss objects without depending on how to represent the objects, geometric ways or intrinsic ways of understanding structures. Computer science has this interesting dichotomy between the concrete and the abstract. Object-oriented programming languages is the idea that if you want to do structured programming, you should distinguish between what are something, and how do you represent things. So an object-oriented program is built from classes. Classes has these specifications of the operations. Linear space should have addition, should have a scalar multiplication, should have the possibility of applying linear maps and so on. There's a specification of what to do. And then there's a private part of the class, which is the implementation, the data structures, the algorithms working on the data structures. That's the how part. And in computer science, it's important to divide between these two, because if you build a big software system and your classes is constructed this way, and the classes only communicate with other classes through this public specification, this upper part here, the specification of what to do, the signature of the object, then one can redesign the private parts later without affecting the total system. It's not destroying the implementation to go in and modify. You can move from dense matrices to sparse matrices and so on. And then you have to be a bit careful, because some algorithms would be able to relate to computations on this upper level, and other algorithms would need to know particular data structure to operate efficiently. So for, again, linear algebra, if you want to solve linear systems by Gaussian elimination, then you really need to know the matrices, how they're represented, if they're sparse or if they are full dense matrices, and Gaussian elimination would need to know the inner workings of this linear algebra class. Whereas there are other algorithms like these iterative methods for solving linear systems that only relate to computing linear operators and perhaps also computing some approximations of your matrices, preconditioning and so on. So some algorithms can live on this top level, others need more information about proper data structures. Unfortunately, and that was probably why I moved from computer science to mathematics. Computer science is very little interested in continuous mathematical structures. The students of computer science don't learn analysis, so it's not easy to work with students of computer science when you want to do numerical analysis. But this idea of classes and this distinction between what and how, specification and implementation, is something that we really took very seriously in the 1990s for topics of computational mathematics. Within computational mathematics, can we take this distinction between specification and implementation seriously here? We call this effort coordinate-free numerics, and it was really an effort to see how much of computational mathematics can be lifted to this level of things relating only to intrinsic geometric operations, which we did pursue in the various contexts. I will discuss one of them here. So gradually, in the 1990s and after 2000, it became, I would say that computational mathematics matured in these decades for several reasons. We became aware of the power of abstractions. And we, of course, with modern programming languages, you allow for programming things abstractly. Category theory is a topic that is taught in computer science departments because it's used to understand certain computing languages, programming languages. Global analysis, coordinate-free formulations of differential equations are useful to finding right abstractions for looking at what are the essential elements of a computational process. On the other hand, I would say that there's, as we will say, there's an interaction here. So the abstractions we need for doing computations are also enriching the more pure mathematical view of these structures. And a focus on fundamental geometric and structural properties of the problem helps the design of qualitatively better algorithms. That was really the effort of geometric integration in the last couple of decades. First example, which I will just mention briefly without going into any detail, is this topic of finite element analysis. So finite element analysis is structural problems, solving partial differential equations where you do it by triangulating your domains. These three people revolutionized the area of finite element calculus by introducing what is now known as finite element exterior calculus, where they take seriously the more abstract mathematical view of differential operators as differential complexes, and by doing this in a geometrically good manner and discretizing these spaces in nice manner so that you have commutativity between the operators on the continuous and discrete levels, they created a new theory explaining many old finite element methods and also getting new results. So new results on stability of finite element discretizations came from this view of finite elements as a discrete exterior calculus problem. So in numerical scientific computing, computation science, this has really been rather influential, but I'm not going more into this. Let's come back to Kepler, because that's a fun problem to show the effect of structure preservation. Let's try to show a numerical experiment. So what we are seeing here is the 5 outer planets, if you consider Pluto to be an outer planet. And we will see the first method is Eulers Method. You just know in which direction the planet is moving. You have the tangent, you move 10 days in that direction, get a new point, move 10 days, 10 days, 10 days. That's the result of Eulers Method to the planetary system. Started in 1990s, integrating to 2100 about. Then Saturn is thrown out of the solar system. They increase energy. Saturn is thrown out. This is the energy of the system. It should be preserved. This is the angular momenta of the planetary planets. It should be preserved, but it's drifting. Rotational symmetry should give preservation of angular momenta. So what you learn in basic numerical analysis 101, you learn that Euler's method is unstable, so you should use inverse Euler, where you compute the tangent in the next point, and you move backwards to find the tangent from the next point that goes to this point you started. It's an implicit method. The inverse Euler works like this. Not better. The planets spiral inwards instead of outwards. Now, Jupiter is thrown out. You have the jump in energy when Jupiter is thrown out. You have a drift in the angular momentas again. Miraculously, third method, you should know that there are 6 components of each planet. There are 3 positions and 3 momentas. Now we use forward Euler on the positions, inverse Euler on the momentas, which is, in classical sense of numerical analysis, shouldn't be better than the other 2 methods. It's just the same local error per step, so it shouldn't be a major deal. But this is this symplectic Euler, where you use implicit Euler on the momentas, explicit Euler on the positions. They go in elliptic orbits, as Kepler told us they should do. Energy is fluctuating slightly, but it's within bounds. It's 10 to minus 4, so it's just slight variations in energy. And angular momenta, 10 to the minus 15, it's just machine precision. This is perfectly preserved. Why? Because there is a structural property of the system that this last method is preserving. And if you don't care about structure, you wouldn't understand this. But once you start looking into geometric structures, that was Kepler's problem. It was first forward Euler, then it was backward Euler, then it was the symplectic Euler. This symplectic Euler has this nice property that if you analyze it, there is a structural property of this system. It is the system of so-called Hamiltonian equations. They look like this. You have a total energy, and the positions evolve according to the derivative of the Hamiltonian with respect to the momenta, and the momenta develop according to minus the derivative of the Hamiltonian with respect to the positions. So these are Hamiltonian equations, a very geometric thing. there is some geometric structure, something called a symplectic form, which is a kind of inner product on the phase space here. And it should be preserved, energy should be preserved, and this symplectic structure should be preserved. This symplectic Euler preserves the symplectic structure, not exactly the energy, but it preserves the symplectic structure. And because of this, you can prove that the symplectic Euler solves an equation of exactly the same form, but where all numerical errors are just a perturbation of the Hamiltonian function. So you will have an exact solution of a perturbed Hamiltonian system. So it's not an arbitrary perturbation of the system, it's a perturbation within the class of Hamiltonian systems. Hamiltonian systems, you know, things like Hamiltonian being preserved, symplectic structure being preserved. And in this case, it is a perturbed Hamiltonian that is exactly preserved, and that's why, since these two are not exactly the same, we saw these small fluctuations in energy. This was a very good example of structural preservation that really led to a change of attitude in numerical analysis. This was done by Feng did these kind of things in China in the 80s, and Chu San-Serna did it in the 90s for Munthe-Kaas methods. This led to all these activities on geometric integration of dynamical systems, where we were studying what sort of geometric properties of a dynamical system can be preserved under discretization, what cannot be preserved, and how do you do it, how do you devise algorithms that has certain qualitative features. We are very fond of studying this kind of schemes, which is a generalization of this basic Euler method. This is Euler, you just compute the tangent and you move forwards. These are called Runge-Kutta methods, where you gather information around the base point. You're in the base point yn, you gather information around yn, you somehow combine this information and step ahead. This is a class of methods where you have certain coefficients, bi and aij, and you really want to design these coefficients so that you get nice geometric properties. And it turns out, surprisingly perhaps, that a lot of these geometric properties can be understood by analyzing this system. And a lot of work was done on many types of structure preservation. For Hamiltonian systems, it's a preservation of symplectic structure. You could also design methods that preserve energy, or the first integrals, preserved functions on the phase space. For systems with divergence-free vector fields, you know that the flow preserves the volume, so you would like to do that. There are Lyapunov functions. There are restrictions of functions evolving on manifolds, like spheres or more advanced manifolds. There's the preservation of symmetries and various symmetric properties of dynamical systems, preservation of fixed points. So a lot of activity was going on, and it turned out we were able to devise good algorithms for some of this, and we were able to say for others that no way, it's not possible. For instance, for mechanical systems, it was well known after some years that you can preserve symplectic structure, this kind of inner product on the space. You can preserve energy, but you cannot do both of them at the same time. So that's no-go. For volume preservation, you can preserve volume, but you cannot, it's actually still an open problem. Can you preserve volume and still be equivalent with respect to all rigid motions of the space? It's not clear. So there are many ways of constructing numerical methods. I will not go into details, but I will focus on one class of methods that we developed. It's a collaboration between Bergen, my university, Cambridge, and Trondheim, with quite a lot of people. Essentially, a lot of it was done in the decade between 1995 and 2005 or so. For me, the basic question was how to take this separation between specification and implementation seriously in dynamical systems. The basic problem is, if you look at things like Runge-Kutta methods, that you do things that does not make sense on the manifold. You have a coordinate, you add a tangent vector, doesn't make sense. And so you have to rewrite these things in terms of natural operations on the space. So starting with the Runge-Kutta method, we have to give some information. If we have a velocity on this space, we have to give an information about how can we move in that direction. So the basic assumption I started thinking was, okay, we assume that we can have a group acting on the domain. So like if you're in a sphere, you can have a rotation acting on the sphere, and it gives a way of having a unique direction you can compute from given just a tangent. And you use this information to devise a numerical integrator. So I'm not going to, I don't want to go into details, but essentially what is done here is it's taking this Runge-Kutta method and replacing things like translation on the domain with group actions on the domain, and writing the equation in a geometric way, independent of coordinates, by considering mappings from the manifold to the Lie algebra of the group acting. This gave a scheme of this kind, and in order to get high order, one has to involve something called computators, which, in a sense, if you translate on Rn, it is so that if you translate in two directions like that, and you do it in the opposite order, you come to the same point. In linear space, a plus b is the same as b plus a. On a sphere, if you do rotations, you will have a difference between rotating here and rotating there, or doing it in the opposite way. This is these commutators, and they need to be taken into account to get a high-order method on such a homogeneous space. But it was done, and it was possible. And it was quite surprising to us that you could make a good theory of such integrators in such a way that all the classical theory comes out by just plugging in Rn and the action of Rn on itself by translations. So it's a true generalization of the classical methods, which one could use, for instance, to solve Sturmer's problem. It's a really powerful thing that you can plug in any group action here. So what is a group action for Sturmer's problem? You have to look for something that you can compute exactly. And what you can compute exactly is, in the case where the magnetic field is just parallel like here, then the solution is just a spiral along this magnetic field like here. So this is a group action. If you have a tangent here, you can move it, and you know that it's here after a while. So you can move it along this action. You can compute these brackets and so on, and you can plug it into the machinery, and you can get a numerical integrator for Sturmer's problem. What does it look like? It looks like this. This is Sturmer's problem with a Lie group integrator. Here is Bergen, where I now live. This is Tromsø, where I'm going to work now, and we'll see very soon why I'm moving to Tromsø, because of a new center called the Lie Sturmer Center for Mathematics. So this is okay. So it was just an example of a Lie group integrator, and for things like this problem, these kind of methods are more efficient because things can be computed fast. These rotations can be computed fast and so on. And you can take much longer steps. This is the step size you can do with a Lie group integrator. This is a step size you can do with the classical Runge-Kutta method. And you can take something like 8 to 10 times as long steps because a lot more of the geometry is contained in the formulation. It's also so that you can devise methods that preserve certain first integrals by choosing a good action. If you're doing mechanical systems, you can use things like something called co-adjoint actions and so on, and devise methods that are, by construction, preserving certain qualitative features. I have to start rounding off. I think I will spend about 5 minutes more. Let us say a little bit about the analysis and where this connects to geometry and so on. So classically, the way we analyze things like Runge-Kutta method is by expanding it in a special type of Taylor series. This is a Taylor series which is indexed by trees. For each tree we have an elementary differential. So we are solving the equation with this little f being the vector field of our equation. And for this vector field, we can, for each tree, get another vector field by taking components I, component j of the vector field, component k of the vector field, and differentiate this with respect to I and j. So if this is I, j, and k, then we get these elementary differentials as the basic elements of this expansion. There are certain coefficients here. And this kind of expansions go back to Cayley, Arthur Cayley, 1857. But they were not really investigated until about 100 years later when John Butcher was studying these kind of things. And he found that there was a lot of algebraic structure in these coefficients. So there were nice algebraic operations of describing things like composing two methods, taking the inverse of methods, doing the so-called backward error. If you have a numerical method and you want to find what flow is going, what continuous flow is going exactly through your points, that is a backward error problem. All this had nice algebraic descriptions. So B series, classical B series, has a long story going back to Cayley and Merson and John Butcher. And then in '63 there were other works on something called pre-Lie algebras, which is an algebraic structure. And it turns out that once we start to think more about the geometry of this kind of series, it is clear that these series are really related to something called connections on manifolds. Descriptions of how to parallel transport doing covariant derivatives is important for understanding this series. And all these classical B series, these kind of things, are related to Euclidean spaces. And we were thinking a lot about how to generalize these to other settings. Lately, it has appeared in things like renormalization in physics, in rough path theory in stochastics, and in regularity structures for stochastic PDEs by Martin Harrer and colleagues. So we were considering geometrizations of this kind of series, and did have done a lot of work on this over the years, and are gaining more and more insight into this. So what we really see is that this kind of series are really come in different flavors according to what sort of geometries you are working on. So if you're just on the manifold, as we saw in the first slide, you don't have any notion of parallel transport. You can do the classical Lie series, which is a basic Taylor series on a manifold. This is not enough to understand numerical algorithms, because it's not enough to understand what's happening if you have a tangent vector and you want to move in that direction. So things like group action, or having a connection that describes so-called geodesic curves and then parallel transport on geodesics. These kind of things need more information. So you need this connection on the space to be able to talk about parallel transport. And when you have the connection, you can talk about curvature and torsion of the connection, and then you get different flavors of the underlying algebras, where flat Euclidean spaces correspond to just standard translations on Rn, where you have these connections that is flat and torsion-free, and give rise to something called pre-Lie, which was what appeared also in the works of Gerstenhaber in 1963. Wienberg. If you are on a Lie group, continuous group of like a rotation group, then you have a natural connection which is has a parallel torsion and zero curvature. Here is an underlying algebra called post-Lie, which has appeared rather recently. It appeared in abstract algebra around 2006, and it appeared in our studies of numerical integration on Lie groups around the same time under another name. And then you have cases of things like symmetric spaces, like spheres and so on, where you have a constant curvature and no torsion. So really this slide is just showing that the analysis of numerical integration methods gives input also to the more geometric understanding of mathematics. And the motivation comes from understanding numerical integration methods. This is my last slide. My claim in this talk is that computational mathematics is contributing significantly to unification of mathematics because it brings in an aspect that is bringing things together. So we see this unification in many areas nowadays, like in more pure mathematical topics like commutative algebra. We see that modern books are transformed by computational issues, algorithms and software like computing in Grosvenor basis and so on. So computation in algebra it's something that brings something new in and unifies with other areas. In differential geometry, I claim that this expansions we're doing is giving something new into the game. We are seeing new algebras coming up. They are interesting in their own right. For us, they're motivated by problems in computational mathematics, but they turn out to have nice, interesting properties that might be important in other areas. And we see that they're coming up, this post-Lie and so on is coming up in the study of stochastic PDEs. Computational topology is an area of mathematics where pure mathematics is coming into applications by understanding big sets of data in things like you have point sets and you want to give geometric information to point sets and you do it by growing balls around the points until you get some geometric structures like an annulus here and like a ball here and then they look at this persistent homology, what sort of holes live under large scales of scaling of these points. So the main claim of today, the focus on computational issues, algorithms, and structured software is contributing to the unification of mathematical sciences in the 21st century. I think it's a very interesting topic to combine pure and computational mathematics. It gives a way of discussing between different cultures. It's not easy because languages are different and so on, but I think it's fruitful and I think it's bridging things together. So this is why I'm now interested in going to Tromsø, because we are establishing now a new research center where we will focus on these interactions between computational and pure mathematics and develop this. So I think I stop at this point and thank you again for a very nice invitation.
Solid.